Okay, well, there seems to be a bit of confusion about resonance structures, even though we went through it in class. They are quite confusing. They're a little bit new. So I thought I would give you a couple of pointers, okay, on what we are looking at. And the key thing that I think you really need to remember is this is what we're doing when we realize there is more than one way to draw a valid Lewis. Okay, so there's a couple of examples that help us think about this. So I'm just going to do them on this title slide and then we'll look at them in a little bit more detail. But essentially, it's when we come to figure out what to do with our Lewis structure. So one example is ozone, which is O3. Okay, so if we go back to the rules for our Lewis structure, I know that I need to put three, three oxygens together. Now these oxygens, okay, are going to have 6 electrons in their valence shell. Okay, so if I have 3 of these, if I have 3 lots of these, I'm essentially going to have 18 valence electrons that I need to put around my 3 molecules. So they're going to have to be joined together. So first of all, let's join 3 oxygens together. Okay, so here we go. I've got these ones joined together, okay, and I'm going to have 1 electron from each oxygen forming my 2 bonding pairs. Okay, so now that's 2. Now we know that each oxygen likes to form 2 bonds, so this oxygen in the center is okay, it's got 2 bonds formed, but this oxygen out here is not okay. Okay, so I've used up 4 electrons. I've got 14 still to use. So if I put my lone pairs on this guy, okay, and I put my lone pairs on this guy that I know that they're going to want to have from being paired up here, I now have 2, 4, 6 electrons around this oxygen. It's going to want another electron, okay, it's going to want another 2 electrons, so we're going to give it another bond, okay. So now it has 2, 4, 6, 8. Okay, it's got 8 electrons. The one in the middle has 2, 4, 6. I haven't put any lone pairs on it. It's definitely not going to want to make any more bonds. It's already made one more than it would normally feel comfortable with. So now I can put a lone pair on here, 2, 4, 6. 2 on the central atom is 8. Okay, this one over here, if I look at this one over here, 2, 4, 6, it's not got enough electrons, but I have 2 electrons left because I've got 2, 4, 6, 8, 10, 12, 14, 16. I've still got 2 more electrons left, so I can actually put another lone pair on here. Now, if we look at that, that seems a little bit unusual, okay? Because that wouldn't be that stable. And it's true, it wouldn't be that stable. Things meet the octet rule, but the central oxygen's got 1 more bond than it would really like to have. This oxygen over here has 1 less bond than it would really like to have. So this is where we start to see resonance, okay? So we have this ability where we've got this double bonded oxygen and a single bonded oxygen over here. We have this ability where those electrons start being bounced across between all the oxygens, okay? So what happens is these electrons here, okay, out on this one here, on this oxygen, which we have 3 lone pairs, which is pretty unstable, 1 lone pair is going to jump into here. What that's going to do is shuffle around a bunch of electron density, and it's going to actually repel the electrons in this double bond up onto this oxygen, okay? So what that's going to do is we're going to end up with this oxygen now has electrons that have pushed into here to form our double bond, our central oxygen, and then we've got this guy, and then the electrons that were in the double bond have pushed out to a single bond. Okay, so these are our 2 resonance structures. That double bond can swap from being on this oxygen over here to that one over there. Okay, so we call this a resonance structure, the 2 possibilities. Okay, we can see that also with something if we look at carbon, the carbonate anion, or anywhere where we have like the ethanoate anion, so such as this one. Again, we see this double bond O, O with some extra electrons on it because this time we've got a negative charge. Okay, so that negative charge can push into here, push that one up to there, and make that one negative. So it can bounce between these two forms, and that's what we mean by resonance. So let's look at some of the other structures that we need to know. Okay, one of the key ones is benzene. Okay, so we've talked about this where we have the benzene is a 6-bonded ring, so it has the formula C6H6. Okay, and then what we get is this alternating pattern of double bond, single bond, double bond, single bond, double bond. But if we put those on the alternate carbons, we get this structure here. But what we discover is that the overall structure is a resonance hybrid, which is somewhere in between the two. Okay, so we show the two different possible resonance forms by using the double-headed arrow, and we draw a resonance hybrid which can show the blending of each of those forms together. Okay, so this is benzene, okay, which is one of the key ones. And essentially what we're saying is that these electrons are delocalized around the ring, okay, or that these electrons here are delocalized across these bonds in the ozone molecule. Okay, so we've talked about delocalized electrons in metals and things like that. So essentially the electrons are moving across this region or around this ring. They're constantly moving. Okay, and this slide here is essentially explaining that we can see this experimentally, okay, because we would expect the carbon-carbon bond length to be 140, in benzene, it is found to be 140 picometers, which is in your data booklet. So the carbon-to-carbon double bond, okay, this one here, would normally be 134 picometers, okay, and a single bond would be 154 picometers. And we don't see 134, 154, 134. What we see is all of them have the same bond length of 140 picometers. So we know that it can't actually be one of these two resonance structures. It's something in the middle, and our bond length is in the middle, okay? And then we have the delocalized electrons. So let's have a look at it. Definitions that we need to know. Resonance is where we have two or more Lewis structures that to represent a molecule or ion. So essentially these are Lewis structures, okay, that meet the bonding rules. Okay, having a complete octet or completing the valence shell. Okay, a resonance structure is one of the multiple alternatives that we can have for those Lewis structures, okay, and is only one. And then delocalization is the electrons being shared between more than two atoms or across two atoms, okay? So like in ozone, it's going to be shared across the 3 atoms in our ozone molecule. Okay, so examples that we should be aware of. Anytime we have this C double bond O, O out to a negative, okay, so anytime we have a negative ion like an ethanoate or methanoate, we will have a resonance hybrid that bounces between these two oxygens, okay. Ozone, absolutely critical to know, and we will do some more work on ozone in a later unit, okay. Nitrate anion, so we can have, if we're looking at doing nitrogen, our Lewis structures, remember nitrogen wants to form 3 bonds, and in this case it's actually going to form 4. It's losing its lone pair electron, which makes it a little bit unstable, so it bounces these electrons around the oxygens on that central nitrogen, And again, we get this bond length that is in between a double and a single bond. Okay, if you want to watch a little bit more on benzene, there's a video there for you to have a look at it, okay, which goes into more detail than you need to know. Okay, formal charge and everything like that we cover in HL chemistry, so it's not something you need to know for SL at this stage. Okay, this goes through ways for you to spot resonance, whether or not resonance will be possible. Okay, what we usually see is where we have a double bond to a carbon atom with an adjacent atom with a lone pair. We need to be able to stabilize this lone pair. So the ones we've seen mostly have oxygen to another oxygen that's negatively charged. We can see resonance with nitrogen as well. Okay. So these are some more tips on figuring out resonance structures, but mostly if you get a handle on the ones that the IB asks you to memorize, which is your carbonate, your ethanoate, benzene, and ozone, you should be okay. Okay, so in this structure here, we don't have resonance because there's no adjacent atom with a lone pair on it. Okay, so when we jump to this structure here, we do have resonance because we've got these two oxygens. Okay, here with the carbonate anion, again, we have all these oxygens here that double bond can bounce around between all the different oxygens. Okay, with resonance, there's usually a minor contributor, which is the less stable version, and a major contributor. You will not be asked to specify which is the minor and which is the major. Okay, you just need to identify resonance at this stage. Okay, so that's it. I know resonance seems quite confusing, but remember that we see bond lengths that are in between a true double and single bond. We have delocalization of electrons, and that our most common examples of this for the SL course are benzene, ozone, and then things like our carbonate and nitrate anions. Okay, so good luck with that, and hopefully this helps clear up some of that confusion.